Today's speaker does not really need an introduction. Our Matthews will talk about iron acidification and isotopes in supraphone material in the Mediterranean. And a few announcements. Tomorrow at 10 o'clock in one of the rooms over here, there will be presentations by the master students, 10 to 12, Sandra? Yeah. Also tomorrow at 12, the cow seminar will be given by Erez. He'll talk about the semi-analytical model for short-range near-ground dispersion. Next week, we'll hear from Beverly Goodman from Haifa University. She'll talk about anthropogenic influence on the preservation of tsunami deposits. And heads up for a special seminar in July 9th at 10 o'clock by ZFS. Thank you.
Okay, I just put up this slide on banded iron formations, but in fact I'm not going to talk about banded iron formations. I just thought it was a nice picture to start. My talk is going to be about the oxidation reduction conditions in the ancient oceans, and particularly about reduced oceans, and how we can use sapropels, particularly sapropels called S5 and S7, which are Eastern Mediterranean organic carbonate sediments, as modern analogues to calibrate the conditions of the ancient oceans. The redox conditions in the ancient and modern oceans become a question of great importance. First of all, in our understanding of the origin of the oceans, and secondly, with the changes going on in present-day oceans. And in this talk, I'm trying to make some kind of connection between what we see on sapropels and how they can serve in some ways as modern analogues for ancient oceans. This is based mainly on the lovely master's thesis of Ayana Benkovic on isotopes in the sapropels, and also in work that she did after she completed her master's with Simon Bolton in Leeds on what is called epispeciation. And this epispeciation work has been a complete eye-opener. And I want to mention the colleagues from the Geological Survey, Mira Abner, and especially Nadia for all the hard work she put into doing the iron isotope measurements. And iron, as anyone knows, is a troublesome element to do. And finally, Simon Bolton from the University of Leeds was one of the leading figures in the whole of the understanding of past oceanic conditions. And I've had a lot of talks and exchange with Simon over the last 1 or 2 years, and I don't think I've said anything he doesn't know, but I've learned everything that he knows. So we start off with the point is that the Archean and early Proterozoic oceans were anoxic. They were without oxygen. And the widespread formation of fixed sedimentary sequences of called iron formations, sedimentary sequences, are an expression of this anoxicity. And we find them in all the ancient cratons, Australia, South Africa, Canada, the Baltic. But these massive banded iron formations died out about 1.8 million years. And this was thought to be part of what's called the traditional model for evolution of the Earth's oceans. The Earth's oceans in the Archean into the Proterozoic were thought to be earthy rich. They're thought to be ferruginous. This is this first diagram here. But then, at the cessation of banded iron formation, apart from a little bit connected with snowball Earth episodes in the late Cambrian, it was thought that with the rise of oxygen in the atmosphere, the oceans became oxygenated. The rise of oxygen in the atmosphere had occurred about 2.4 million years. But Donald Canfield, about 20 years ago, argued that this oxygenated Proterozoic ocean is not true. He argued that the levels of oxygen in the atmosphere were too low to produce much sulfate by weathering. And this sulfate that was produced in this Proterozoic atmosphere would have been converted to hydrogen sulfide by bacteria in the Proterozoic ocean, and therefore that in fact the Proterozoic oceans were euxinic. They were dominated by the presence of hydrogen sulfide. Apart from this very wonderful episode at the end of the Precambrian, what's called the Neo-Proterozoic, from about 700 million years ago, when suddenly they identify a period of ferruginous ocean. And I'm going to focus on that as part of my talk. Now, what do we mean by ferruginous and euxinic? It's basically domination of iron 2, Fe2, which is reduced iron, or H2S in the ocean. So when Fe2 plus is dominant, we have a ferruginous ocean, and the minerals that we will see will be iron carbonates, magnetite, and some pyrite from this sulfide here. But when we talk about euxinic conditions, we're talking about the dominance of H2S in the water, less Fe2, and basically this Fe2 will react with the dominant H2S to produce pyrite. So we're talking about a pyrite-dominated mineralogy in an H2S euxinic ocean. Now, how does a few words now about techniques. How basically did people come up with ideas of how to measure ferruginous versus euxinic? And it basically came from studies that are known as Fe speciation studies. And I won't go into the details, but basically the idea is you do dissolutions, sequential dissolutions using different chemicals, and you extract the various mineral components from the iron mineral components from the rock. So what is Fe2HCl would be acid volatile sulfide or ferrous carbonates. Fe3Cl is either a very unstable mineral called ferrihydrite or oxidized pyrite. FeOx would be hematite and goethite. FeMag would be magnetite. FePy, extracted with chlorus chloride, would be pyrite. And then you have the total analysis, which is everything, including any iron silicons. Now, these four components here that you extract by this sequential chemistry give what is known as the highly reactive ion. Highly reactive ion is simply the sum of these various components of the extraction. And it is basically considered the iron that is available for reaction, readily available for reaction with hydrogen sulfide to form pyrite. So it's the readily reactive to sulfide part of the iron. Now, there's something special about sapropels that is important. Sapropels are sediments that are extracted in cores. They're not preserved in nitrogen. They're not preserved in anoxic conditions. So very often, the pyrite undergoes oxidation, and they're stored in frozen but in open atmosphere. So part of that, this pyrite has already been converted to some kind of oxide product. So to measure this, basically what we do is combine the Fe pyrite that is measured here with this Fe3HCl, which is this, and this gives a maximum estimate of the amount of pyrite that was there in the rock at the time of formation. So these things are combined in two diagrams which Simon Colton or Colton Canfield developed, which tell us whether waters were anoxic or oxic, or whether they were euxinic or ferruginous. And basically, the first diagram is FeHR over the total, the highly reactive ion over the total ion, and this is defined into the areas where ratios of this above 0.4, the waters are anoxic, they have no oxygen. Below about 0.22, they're oxic waters, and we have this grey area or yellow area, which they could be either or in between. So this one ratio tells us when we're having anoxic conditions, and when we do find anoxic conditions, we move to this diagram, which is the ratio of pyrite ion to the highly reactive ion, and then up to a boundary of 0.8 in this ratio, we're talking about ferruginous, Fe2-rich waters, and above 0.8, we're talking about euxinic waters. Now, all these calibrations were empirical. They were based on the rock record. They were based a lot on the Black Sea, which is a euxinic sea. And this figure of 0.8 here was developed from the Black Sea. And this is what was used by Canfield, Colton, and others in all their investigations of the ancient oceans. Later work showed that you may lower this boundary to about 0.7. And this was done based on, basically on analyzing euxinic rocks from oceanic anoxic events in the Phanerozoic, in other words, in the non-Precambrian time. And I'll say a little bit more about this. But the work that was done by the pioneers of this field in ancient oceans used this value of 0.8 as the boundary. And here is the slide for the late Neoproterozoic, which is very influenced in saying that there were ferruginous conditions in the seas. The first diagram is the standard FeHR or FeT plot, and as you see, a lot of the samples, I won't go into the detail, are oxic, but many of these samples from deep basins and from non-year shelf samples are in the anoxic field. And when these anoxic samples go into the second diagram, which is the pyrite diagram, pyrite Fe diagram over the highly reactive, one sees actually that throughout a long period of time, from about 700 years down to about 550 years, the ocean was ferruginous. It's below this boundary of 0.8 that was derived from measurements in the Black Sea. So this is the basis, of the 700 to 500, 550, 650 million year assumption or proposal that the oceans became ferruginous for a 200 million year period of time. On either side of these periods, the oceans show evidence of euxinity. Okay, here, this is something from this called the Chur Formation in Colorado. And these circles here, at the very end of the Precambrian, the start of the Cambrian, are from the Yangtze Plateau in China. So they basically, and these are hundreds of samples they took. And so big, and all of them all over the world. And so you move from euxinic to ferruginous, and then back finally to euxinic, before the modern day oxic oceans developed. So the model of the Precambrian ocean starts off with the early to late Archean, with a ferruginous ocean. When we come to the period from when oxygen may have started to appear, you started to see euxinic waters, but the waters were dying, so it was still ferruginous until 1.8 million years. And then from 1.8 down to the start of the Cambrian, we have a dominantly H2S ocean, as Canfield proposed, but you have these periods, like this period in very late Neoproterozoic, 200 million years, when the oceans became ferruginous. Another point, the next point I want to note from this diagram is that the source of iron into these basins was assumed to be hydrothermal. From hydrothermal vents, from mid-ocean ridges, spreading centers, but the source was assumed to be hydrothermal. Now this, in fact, is not necessarily the case. And for this, I just want, my second technical slide is just to say a few words about Fe isotopes. Fe isotopes are measured as the ratio of mass 56 to 54. And we use the same notation, the delta notation per mil, as used in oxygen isotopes, hydrogen isotopes. And basically, the major fractionation event in iron minerals is between oxidized and reduced minerals. Okay? So this is increasing with delta 56. The fractionation between iron in solution and iron 3 in solution, Fe2 in solution, is about 3 per mil. And this difference more or less reflects the minerals, the oxidized iron minerals with Fe3, like Goethite, hematite, and this is very hydride, are all heavy, whereas the iron 2 minerals like chlorite, iron carbonate, and even magnetite tend to be light. So you have this fractionation, and generally the fractionations are about 1 to 2 per mil, not as large as this 3 per mil. But there's one point I want to say is that when you go from Fe3 to Fe2 across, say, what's called the chemical line, and you convert all your Fe3 to Fe2, then you won't see a fractionation. 100% conversion from one system to the other system will result in zero fractionation. In other words, new phase will inherit the composition of the parent. But otherwise, in any situation of partial transfer or mobilization, you will see a fractionation between the reduced and the oxidized iron phases. And this is the basis of what's called the benthic iron shuttle, which is the last new concept I want to introduce. This was introduced about 10 years ago by Lyons and Shuttle and Settlement. And the idea is that you have a shelf and you have a deep basin, and in this deep basin you have H2S. And iron on the shelf will be mobilized by reductive dissolution and form all sorts of phases, Fe3, Fe oxides, Fe2. And these will be transported, and when they come into reducing conditions, they will all be converted into Fe2. And this process will result in adding light, isotopically light Fe2 into the ocean. Okay? The iron oxides that are oxidized to Fe2 will be become isotopic light Fe2, the light Fe2 comes straight, is itself light. So you're adding iron and you're adding light oxygen, isotopically light oxygen, during this shuttling, called the benthic shuttling of iron from the shell into the deep base. So you'll be adding, and of course that iron, when it meets the H2S inside the basin, will form pyrite, and this pyrite will be light. So you're adding isotopically light pyrite into the basin. Now this is a model. The model was just derived in about 2000. Well, it was started derived in about 1996. But basically, Sedman in 2008 showed that it's true. When you look at the Black Sea on a diagram of delta 56 versus FeAl as the monitor, and this is the total on the bulk. Here are the values on the shelf, which are normal delta Fe values about 0 to 0.2 per mil. But then when you come into the oxic and euxinic basin sediments, you see this increase in FeAl and the decrease in delta 56 due to this added exported light iron into the basin. So the model works in terms of its chemistry. And the question is, when did this start to occur in the oceans? It's an open question. So now we turn to sapropels. Okay? Sapropels are organic carbon-rich sediments that form periodically and are connected with maximum insolation periods, high solar insolation. And this leads to very strong monsoon rainfall and also to increased westerly rainfall. And the net result is that the Mediterranean changes. In the normal Mediterranean eastern parts of the Mediterranean Sea, the saline, the very saline waters that form at the surface through evaporation, draw down, taking oxygen with them, and create what is known as thermosaline circulation. That's the normal state. But in the sapropel time, the massive input of fresh water from the Nile River, ephemeral rivers in North Africa, from the increased rain on the sea, creates a surface layer of fresh water. And this fresh water acts as a stop, it prevents the saline water developing and shuts down the circulation. And this shutdown of circulation means that oxygen is not getting to deep waters and they become anoxic. And it is under these conditions that we see sapropels forming. This is the site we chose. It's a site that is a core ODP 967 at about 2.5 kilometers, just south of Cyprus. And as you see, it's in the eastern Mediterranean basin with its sill. Here you see the present salinity. This is the high salinity that is causing the thermal haline circulation. These saline waters are sinking and promoting the circulation of water in the current Mediterranean. But in sapropel time, everything stopped. Okay, the fresh water layer captured. Also, you'll see this Black Sea, where a lot of the data on euxinic deposition is got from. It's almost a totally enclosed sea, with just a narrow passage into the Mediterranean in Istanbul. It is not like Eastern Mediterranean, which is an open sea in a kind of semi-closed systems situation. Okay. And the sapropels we studied were from S5, from interglacial MIS 5e, and S7, which is from another interglacial. They are both formed at times of very high insolation. They should be strong sapropels, and we should see deep anoxic conditions. Here they are. The latest one occurred in the Holocene, S5 and S7. There are times of very high insolation, and there are also times of interglacial periods. So, at this point, I can turn to the data and the questions. So, the questions are the questions I posed at the beginning. What can the sapropel studies on S5 and S7 tell us about proxies for redox conditions. Were conditions euxinic? Were they deeply anoxic? Did the benthic shuttle operate? And then take the data and see and have a look at how these systematics can impinge our understanding of ancient oceans. So this is the speciation mineralogy for S5 and S7. Okay? I'm presenting them together because, in fact, they give similar results. Here you've got Fe in weight percent. This is depth in the core. So we move from the pre-sapropel sediment to the yellow, which is the sapropel sediment, and then out of the sapropel, 128 to 120,000 years here, about 197 to about 191 thousand years then, and pre-sapropel and post. What we see is a very strong rise of pyrites in the sapropels. We see that iron oxides are also present, and they seem to show some kind of increase. But phases like magnetite and Fe2HCl, which basically represents kind of a weakly ordered ferrous iron carbonates, are very minor. And the same is true for sapropel S7. You see, as you come into the sapropel from the underlying sediment, rise in pyrite, and then it decays to the termination of the sapropel. It's a little bit different from S5, because S5 seems to preserve the high pyrite peak right almost to its termination, whereas in S7 the peak appears to go about 2/3 of the way through the event. So the same story, lots of pyrite and the presence of iron 3 oxides. We're talking about phases like hematite and goethite, iron oxides. Then, if we look at the iron isotopes, now on these graphs I'm showing FeAl here, the amount of iron, that would be the blue line, and this scale will be in red will be the iron isotopes. The normal marine range is about, most marine sediments is about 0 to 0.2. And what we see, apart from this strange rise here, which I won't go into it, I don't really fully understand it, I have an explanation I'll mention. But the main thing I want to show is this drop in delta 56 Fe here in the sapropel. Then it's rise out to the normal range here. That's this scale. So it drops down to values as low as 0.6. At the same time, the iron rises, and it rises more or less in exact opposite to the drop in the iron isotopes. This is the FeAl, this scale is rising, and then falls as you come out of the sapropel. And this is also true for F7. The sapropels are in the normal marine range, then they drop in the iron isotope composition, and then rise out of it, and the FeAl rises, and then it starts to drop. As before with pyrite, it starts to drop within the sapropel about 2/3 of the way through, whereas in the S5, things seem to continue right through to the end. The explanation of this, I think, is that at some stage in the pre-sapropel sediment, there was leaching of isotopic light Fe2 from the sediment, and it shifted the residual sediment up. But it's not part of my story, and I don't say I understand it fully. So, when we look at the benthic shuttle, the obvious seems to be occurring, because we saw it in this previous diagram. So if we plot the delta 56 of the sapropel versus FeAl, we see exactly the trends we expect from the benthic shuttle. Low FeAl values in the sediments, and then the increase in FeAl and the decrease in delta 56 as we go to more and more anoxic conditions. The trend line is parallel to the Black Sea. Okay? The only difference is we seem to be more Fe rich in the sapropel than the Black Sea. And the same is true for Sapropel S7. We have this surrounding sediments like normal sediments, and then the increase in FeAl and the decrease in delta 56 with the sapropel. This is the Black Sea. So the sapropels behave like the Black Sea, with the exception that they tend to be a little bit on the iron side. That's true with sediments, that's true with the sapropel, and this one point out here that it's really iron rich. Yeah.
Fe to sub T
It's total. It's total Fe.
Of all extractions?
Of all the iron in the sample. And with the idea of the benthic shuttle is that Fe, oh sorry, the T should have gone. No, I mean FeTOL. But the idea is that as your iron is going from the shelf into the basin, you're exporting and adding iron all the time, and this raises the FeAl ratio. Alumina is just to normalize it. So the idea of increased FeAl in the benthic shuttle is simply you're shoveling, you're pushing lots and lots of iron from the shelf into the basin, into the deep basin.
But the delta should depend on the amount of distillation, on how much iron you distill down.
In Stevelman's model, the decrease in delta is simply that all this iron that is shuttled from the shelf into the basin is converted to isotopically light pyrite. So the iron that you're adding here is in fact isotopically light pyrite. It's a pure additional effect. They don't even talk about Rayleigh fractionation. That's way into subtleties. The truth is, the iron isotope process could involve Rayleigh fractionation or something. But the idea is that you're just adding iron, and you're adding isotopically light iron, which forms pyrite, and therefore gives you this trend. It's a trend of adding iron, added pyrite. So in this sense, the sapropels behave perfectly according to the model of the Black Sea, of the benthic iron shuttle. But let's now look at speciation diagrams, because this is where the story starts becoming interesting. Now, there are two diagrams. One is the highly reactive iron, or the total iron, and the other one is the pyrite iron, or the highly reactive. And this boundary here, as we saw before from the previous diagram, of about FeHR or Fe total of about 0.4, defines whether conditions are anoxic. So sure enough, S5 is anoxic. It's anoxic. The waters even in the sediments preceding S5 are anoxic. There's a rise, but the major thing is this rise in anoxicity shown by this proxy in sapropel. Then it drops off into what could be anoxic. But when we come, therefore, and take this data and put it into the second diagram, the diagram that separates between ferruginous and euxinic, this is the Black Sea boundary that Canfield and others used. But then later and this is important, they lowered this boundary, or Simon Poulton, I should say, lowered this boundary, and we called it a possibly euxinic. So it means that at this boundary, above this boundary, you can be possibly euxinic. Now, this possibly euxinic boundary was in fact derived from what are called oceanic anoxic events that occur throughout the record, periods in the Earth's Phanerozoic history when the oceans became totally anoxic and they became euxinic. And one of the most well-known of them in our region is the Cenomanian Turonium sapropel oceanic anoxic event, which we don't see in our Cenomanian Turonium boundary, but is very much present in the other parts of the Mediterranean. But basically, when people measure these speciation indicators on the oceanic and anoxic sediments, they found that the boundary should be shifted down. So what Simon calls the possibly euxinic boundary is in fact what is the boundary that's defined by the Phanerozoic oceanic and anoxic layers. And the reason why the boundary drops is simply that the pyrite to HR ratio drops because in these particular sediments there's a lot more iron oxides that deposit with the pyrite, and since the iron oxides are part of the HR, then what happens is this ratio becomes lower. So the idea with this possibly euxinic boundary is that much more of the iron oxides that form in the water column actually escape being converted into pyrites, and therefore they lower this boundary. All this is, of course, relative to the boundary defined by the Black Sea. In the Black Sea, the sulfidization of iron oxide is on a highly reactive iron. It's very powerful. The boundary is up here. When you start looking at the real oceanic and anoxic events, it's lower. And why I say it is really, actually, when you look at the data from the sample pair, it barely crawls into this possibly anoxic sphere. In fact, most of the data are just ferruginous. Okay. But it's close to this Phanerozoic anoxic euxinic boundary, but still mostly on the ferruginous side. And it's the same for, yeah?
What are the error bars on these dots?
Huge, I imagine. on these ratios, I know the errors on individual measurements would be something like plus or minus 5%. That's just measurement of the iron. So I think the point is you have to take all these boundaries with a certain amount of caution. But to tell you the truth, I haven't done a proper error analysis on these ratios. But I guess if I said it was 10%, then it would be.
In our lab, we never do better than 20-25%.
Yeah? Okay. Simon quotes the error on his iron measurements is 5%, so it's a projected error of 5% RSD. But the numbers are consistent with their pattern. And if you look at S7, it's the same story. Again, a rise in the toxicity, a marked rise in the sapropel, and then it's collapse. And again, we see that the data for the sapropel are tending to straddle this euxinic ferruginous boundary. The fact remains, errors or not errors, the data, when you put them on a combined diagram of FEPY of HR versus, sorry, FEHR or FET versus FEPR of HR diagram, the data are predominantly within the ferruginous field with a few data points crawling into the euxinic field. Now, what does this mean? It could be that we're seeing something different. We're seeing evidence for ferruginous ocean conditions. It could be that this boundary is shifted down, and it could be, as Igor has mentioned, that we're also dealing with quite large errors. So this boundary itself would be a very variable thing. But there is this question that the data, when taken at its face value, seems to indicate ferruginous rather than euxinic conditions. Now, could this be possible? Is this so? The question is, we've seen that there is a benthic shuttle. We've seen that we're getting isotopically depleted Fe2 added into the basin. could this be the case? And the answer is theoretically, with the data that we have, one could either propose a ferruginous situation or a mucinic. The ion shuttle has basically two components. The anoxic shuttle, here it's the mobilization of light ion 2. This can be mobilized directly into the basin under anoxic conditions and go into the basin. Or a lot of it will be, of this ion will be mobilized into what is called an oxic shuttle, the oxic conditions, where it will be converted into iron 3 oxides, hematite, and these will then descend. Now, in the normal way, in the acidic model that Sedman proposed, basically all this Fe2 and Fe oxide, iron 3 oxides, and most of the iron oxides will react with the H2S in the acidic basin to produce all this additional pyrite, which will be light and will cause the delta 56 to drop and the FeAl to rise. That's the euxinic model. If one is going to propose a ferruginous basin where one has no H2S, basically to get this light component of iron into the sediment, one has to do a much more complicated model. One has to say that all this isotopically light iron 2 is converted into isotopically light hematite, and then this isotopically light hematite descends through the Fe2 ocean without being reoxidized and deposits on the bottom as isotopically light hematite, which then undergoes diagenetic alterations of pyrite, giving you what you have. So theoretically, a ferruginous shuttle is possible. Did it happen or not happen? Well, I think the balance of evidence basically must favor the established euxinic shuttle. Okay. With the ferruginous shuttle, you have to isotopically light iron, shuttle it down into the basin, forms as iron oxides, they sink to the bottom, they undergo partial conversion from hematite to pyrite, giving you your mineralogy and all your isotope. The major argument against it is no one has seen anything like that today in the modern oceans. Okay. Whereas the euxinic shuttle makes a lot of sense. The idea again is that you have the euxinic waters, pyrite is formed through the reaction of the isotopically light Fe2 with H2S. Some of this hematite escapes this sulfidization and gets through into the sediment. And the fact that we are always seeing this tendency of shuttle to be more Fe-rich than the euxinic Black Sea is simply because its sapropels in the Eastern Mediterranean Sea are very iron-rich. The plastic input of iron minerals, predominantly through the Nile, into the Eastern Mediterranean is far greater than in any normal ocean, far greater than any other ocean in the sea. And so if you have this massive input during Sapropel periods of detrital iron minerals, and then these iron minerals are then buried without undergoing sulfidization in the euxinic basin, then you will have this shift to higher FeAl values because they represented the added excess iron that is coming into the basin. So this would make so this is this point here. This is consistent with excess input of detrital iron 3 oxides into the PM basin. And this was already shown by Bolton and Dow in the paper in Geochemical. There's a lot of extra iron getting in to the Eastern Mediterranean. And this will give us this shift to slightly more iron composition. And there are a lot of other works that I could quote. There's been recent work that has suggested that the benthic shuttle, the euxinic shuttle, also operated during oceanic and anoxic events. And we have other data on molybdenum isotopes, which also suggests euxinic conditions. So I would love this model to be true, to be fun, but the truth is it's very likely that the sapropels are, in a sense, a Black Sea euxinic story with added iron. Why would this be important? Because this ferruginous shuttle model be important. Why is it still important that we study it? Simply because cycles like phosphate would change completely if there was a ferruginous condition. And the mobilization of nutrient elements would change. So it would be of huge importance. So then we come back to this is not here. But then we come back to the slide I showed in the original epiproxy work, the Camfield et al. Work on the latest proterozoa. Okay, they worked with 0.8 as the boundary, euxinic pole, but otherwise proterozoic values of epipyrite over FEHR. Would it, lowering this boundary to the Phanerozoic boundary of the sapropels of the oceanic magma, change much? Actually, it wouldn't change much. It would still leave this period dominantly as a ferruginous ocean. It might broaden out the possibility of more euxinic conditions, the extent of euxinic conditions, say, determination, but basically, even if we accept that this, for at least for Phanerozoic samples, the lower boundaries is better. It wouldn't change much in our interpretation of these neoproterozoic conditions. But there is one other thing that I noticed when I was going through the data. If you look at the Yangtze platform data, the euxinic data, that's the data here, okay, you see that the euxinic events are largely shown by lots of pyrite and ferrous carbonate. Okay. One of the major constituents of these Precambrian sediments is the very strong presence of iron carbonate in addition to pyrite. Okay. So this basically would be the euxinic event here. And in the proterozoic events, one sees much more iron carbonates. Okay. But there is this shuttle here, this euxinic, here, the Chul formation, the 750 years. And here the mineralogy changes. It is not a ferrous carbonate mineralogy. It's in fact dominated by pyrite and hematite. Exactly the same as we saw for the sapropels, exactly as appears to be the case for the oceanic and anoxic events. And so there is a question. It hasn't been studied, there's no answer, but it could be that when we're dealing with a hematite pyrite mineralogy, we are dealing with a continental shuttle. We aren't dealing with iron that's hydrothermally sourced from ocean ridges. So these are basically the points that come out of just this one study. So to summarize, we do see that the interglacial sapropels S5 and S7 formed under deeply anoxic conditions. The pyrite hematite mineralogy, the benthic shuttle, the fact that they fit to the Phanerozoic boundary, they're all consistent with water column euxinic conditions, H2S in the water column, providing we accept that excess Fe is injected into the Mediterranean Mediterranean Sea via the Nile. This is what shifts all the benthic shuttle and, over. And it also shifts the Fe and shifts the Fe Py over FeHR ratio. But we do have the possibility of this ferruginous benthic shuttle. It hasn't been found, but the finding of such a shuttle would profoundly affect the Earth's nutrient cycle, particularly whereas phosphate would be mobilized in euxinic conditions, phosphorus would not be mobilized in a ferruginous condition. And the unresolved question which still needs to be asked is, does the benthic shuttle, and it doesn't matter whether euxinic or ferruginous, does it characterize any of the Precambrian ceramics? Is it purely a Phanerozoic phenomenon? Is it purely in the anoxic conditions that form periodically in Phanerozoic sediments? Or is it a model that we can carry back into the Precambrian and into the source of iron, into the deep basins in the Precambrian? Okay, so that's where I finished the talk. Thank you.
Talk, and I really don't have any argument with you, but I have a long-standing argument with Kempfield and Paul. I think that they sell much more than they can actually deliver. And I have tried to repeat the protocols that they showed before in my lab several times. I've been doing it for many years, and it's very difficult to come up with results which are better than plus minus 20%. If you take the same sample once, then a few weeks later, you come again to the lab and you reprocess it, you get 20% difference in your values, at least. So when you do this, then you're losing all their, maybe it's impossible to answer these questions about the past, because in contemporary samples, we cannot do it. So this, argument about whether it's 80%, 60%, I'm not sure it's really feasible to do this.
Yeah, I've been in contact with Simon a lot, and I think basically he argues we should take these thresholds with a grain of salt. I mean, with an allowance for uncertainty. I can't answer the question of the reproducibility. Well, if we do the data one day, will we get the same data? They've been doing these measurements over many years. The study in 2008 in Canada was something like 500 samples, and this was done over a huge period. And it seemed to give the same general picture. So, I mean, I just compromise in saying that the general picture, Erez and all, is correct, providing you do enough samples. I mean, if you just do a limited number of samples, I think then, from what you're saying, then you have a real problem.
I agree.
Yeah.
How about lowering the boundary to 0.6?
What?
If you lower the boundary to 0.6.
Actually, for these samples, I would have no problem lowering it down to here, simply because of the excess Fe that's coming in from the Mediterranean.
Out of your S5-7.
Yeah, there's so much iron coming in, you're getting so much more, and it's not getting sulfidized out, and you're getting much more HR. So it would be no problem. I think my last opinion with some, we more or less agree on this point, that you can really shift this boundary down. Okay? So, yeah. But the answer is, Simon is giving the Berner lecture in the Goldsmith conference in August, and I think he's talking about these things, because he recognizes that these problems do exist of thresholds, and how you define a threshold. And that's why I wanted to make it very clear that these two thresholds that they use are really defined by different rocks. Well, I don't agree with this possibly mucinic. I think you should put mucinic there, but some because it is a real, to me, at least the Sapropel is showing that it's a real phenomenon. The Sapropel data are showing that you can lower this boundary, that's for sure. The plus is that it's such a powerful technique. I mean, especially you have to combine it with other things. You have to combine it with iron isotopes or molybdenum isotopes, which is a tendency today. By itself, it is a beautiful tool. But given the errors that are inherent in the method, then you have to work with several proxies at the same time. I think that's a very old, normal story. But since these studies were started, they really have kind of revolutionized thinking about the ancient ocean. There's no doubt about that. Yeah,
I would like to add to Eagle's.
Yeah.
I'm sort of psychologically somewhat scared of any criterion which tends to be genetic but uses cookbook definitions.
Uses?
Cookbook definitions. Dissolved in 0.3 in normal HCl for 1 hour or whatever. Yeah. And then it should depend on what sediments you are in, whether the Mediterranean sediments are equal to the oceanic sediments or not.
No, you're 100% right. In fact, there's a paper by Erez that is coming up. It's in press, but American Journal of Science being what it is, it doesn't get preprints. And it's exactly on this issue of where these things work and where they don't work. There are lots of problems. In ancient sediments, you have metamorphism. You also have minerals like pyrrhotite forming. You have all sorts of things. And basically what Erez et al., that's this one here, which is in press, but you can't see it. No one can see it. You can get it on ResearchGate, because ResearchGate allows the preprint of the text that you submit. But it's basically dealing with this issue. When do these proxies work and when do you get completely the wrong answer? And the answer is sometimes in certain kinds of sediments you get very high FePR, this one, but oxic here. And it depends on the actual mechanism. So the answer, I would say, is that you have to be understanding the system you're working with before you can even start thinking about what these proxies could mean. That being said, there is no other method like this that's come along in recent years that can say so much, potentially. So it's a trade-off.
Any more questions? Thank you very much.
I'm saying there's a lot more iron in Subi than normal sequence and brain, and this is why it's not therefore it's shifting all the efforts. And this would shift your parameters. I forgot to say that people said it would shift the parameters to 6 that would give
היי אהלן.
היי.
אני מצטער שזה לא לך, אתה יודע, זה כל טוב, אבל אני חושב ש- they are overselling themselves. ומאוד טובים בסלסמנשיפ, אני חושב שהם מקבלים הרבה פרסים והרבה קוגנישן. אני לא בטוח שיש, אם מישהו יבוא באמת ויקח את הדוגמאות שלהם, יעשה 10 פעמים את אותה דוגמה, הוא יקבל כזה דלטה. אנחנו מנסים לעשות את זה כל הזמן, לקחת דוגמאות מהכינרת. עשינו אותם 3 פעמים, בפלוס מינוס 25%. אז יכול להיות שהם הרבה יותר מאומנים מאיתנו. יכול להיות שהם הרבה יותר פרופשיונל.
No, it's just
אבל
that they don't say.
כשנדיה עשתה בדוקטורט שלה את ה-sequential extraction של soils, שזה היה רק 4 steps, not 6 steps procedure, אתה יודע, תשאל אותה כמה, היא עבדה, ונדיה יודעת לעבוד במעבדה.
But even today, Raiswell writes that you should only use good shale. You should.
אבל אני גם עושה את זה, אני לא צריך את הילד, אני יודע מה יגאל עושה.
לא, אבל יכול להיות שהם כן הצליחו לעשות חזרה.
I mean, Raiswell and those, they consider you have this. They consider these methods only work in organic shales. You have to have at least 5%. Okay, yeah, okay, fine. And they consider it only works in shales with at least 0.5%.
So you have to consider grain size distribution, organic matter content. If you don't do this, then
yeah. The answer is yeah. You're right. I think my understanding is that this is the work of Canfield was beautiful in terms of
the concept. Yeah, I think it's a concept. Yeah.
Whether there was a ferruginous ocean or not is.
רק עוד דבר אחד, אני הולך לשלוח אליך תלמידה שלי שאנחנו עכשיו עובדים על הכנרת, contemporary situation, in order to test all these hypotheses.
Yeah, I think the fresher the sediments, the more difficult it's going to be to get reproducibility. I mean, one of the reasons that they got diagenetic sediments have been lying around for 1 million years and everything's kind of been smoothed off, and what is problematic in that case is using something like the modern day Black Sea as the calibration line. So, you know, whichever way you look at it, it's problematic.
אבל מצד שני, אם אין לך את ההווה, אז בעבר